Right, hello everybody. Welcome. This is a little addendum to tutorial 4, the one on thermal work. And what I would like to do is add an extra step, which is very important, not so much in the learning of the process, but it is important in learning, in actually applying the process in a more professional context, in a more official context. So I've already got grass open here, and I have used the same work set which we were working with temperature. Here what you see is actually the NDVI image. I'm just going to bring up the temperature image that we calculated, and I'm going to show you how to do this without deleting this. So here there's a button for a new display. I'm going to click that, and I'm going to get a new map display, right? I'm just going to put this over here. Let's make these share the screen a bit. Okay, now I'm going to go into the console, and I'm going to directly type d.rast, enter twice. It brings up request, and I want to plot the temperature, so let's use band 10 temperature. It's going to be here. This has all been corrected. Right. Great. Let's bring the NDVI back. So click on the display to be sure it's active. And again, right, and bring that NDVI. There we go. Okay, so I've got temperature here, NDVI. Let's, if you, in case you've forgotten, let's do a little histogram of this raster map. Take an instant to calculate, but it will eventually. So there we go. So now these are temperatures in Celsius, remember, right? Now, what we've done here in actual fact is to calculate the top of atmospheric temperature. Now for the learning process, this is still okay because it gives you a sense of the temperature, but it's not actually that accurate. And if you're going to do this in a professional context, it's important that you take the extra step that we're going to show here to actually transform this top of atmosphere temperature to an actual surface temperature. Now fortunately, it actually isn't that complicated, and people have been thinking about this for a while now. And if I bring up the lecture, right, so I show you this paper, right? This is an important reference. It's one of the better recent ones I find for this. Now, if you recall, I quite intentionally, right, so land surface temperature is equal to the temperature. This TB is the temperature in our raster, and we're going to have to analyze this with the emissivity of the surface, which is given here, and also from this equation, which we're going to transform with the band ratios divided by the logarithm of the emissivity. If you look at the form of this equation, basically you've got the temperature in our raster divided by 1 plus something. So in essence, what that is telling us is that actually the temperatures in our top of atmosphere raster are observed as being too high. Now you have to be careful because, of course, this is just a satellite observation, but when we say top of atmosphere, we don't mean that it is literally the temperature of the top of the atmosphere, which is of course going to be extremely cold. So don't get that confused. But what this equation is telling us is that that temperature is too high. So step by step, let us start reconstructing this and building up that temperature in a correct manner. So we're going to start, first of all, by calculating the emissivity. Now, the emissivity you see here is, of course, it's something that varies for land surface, and overall it's approximated by this very simple equation where we've got an M factor, which is actually quantitatively determined as 0.004, an N factor 0.986, and some sort of ratio of NDVIs. So actually, we have already got that, right? All we need to do is get our NDVI aster and apply this little equation right here. So we're back into grass. Now, so I've got my temperature image, I've got the NDVI image, just to have a look, and I've got the top of atmospheric temperature histogram here, which is a little bit high with a peak at about 32 Celsius. So now we need to calculate a surface temperature, and we're going to start with the emissivity. I've prepared basically from the Estocco et al. Paper, from this paper, so it's important that you cite this. Right, I've prepared the equations separately. So we need to apply this equation on top of the land surface temperature. So this is the wavelength of the band temperature. This rho factor basically is a function of Boltzmann's constant here, Planck's constant, and the speed of light. And finally, the emissivity, logarithm of the emissivity here, is given by this little equation, which is two constants, 0.4 and 0.96, divided by this factor. So let's start. Basically, when you work with these, you start from the innermost section. It's a bit easier. So we're going to start with this one. So the NDVI minus the minimum divided by the range squared. So we're going to need the statistics. Now, an easy way to do this, you've got the NDVI plotted up here, and you've got it in the Layers tab. You right-click on it, and you get univariate raster statistics. I've already done this, you can see, right? So basically we have the minimum, the maximum, and the range. And now we need to extract that PV, that ratio quantity. So we're going to go raster, and we're going to use the map calculator. So name for new raster, we're going to call this PV. Now we're going to have to insert an existing raster map. So we're going to insert the NDVI. Now, so it is, need brackets here, NDVI minus, we get the minimum, so minus, so that's going to become plus 0.72157 divided by what is in essence the range, the max minus the min, so 1.68033, and we need that entire thing squared up, so I will add a set of parentheses of brackets squared up. I'm going to click the override file because I actually calculated this before in preparation, and it's here PV, right, run. It's going to calculate. It is going to take a few moments. Okay, so that was the first part of our equation. Now we can finish the emissivity calculation. So that is simply 0.004 times the PV raster plus 0.986. So you should let this go. You can actually try to have a look at it. Mine is actually going to be calculated, so I can go d dot rast PV, no, not pan, PV. There we go. So that's the modified. It's kind of a ratio NDVI. It is kind of a step to calculating the emissivities. Right, now we can actually change this. So there we go. That calculation just finished. Okay, so now clear this up. New raster is going to be called M. We don't have access to Greek numerals in GRASS, so you might as well use something a bit more simple. So that was insert a raster map PV times 0.004 plus 0.986. Is that correct? Just checking. Yes, 986 multiply plus. Okay, and that's our estimate of emissivity. So it's writing. See, the ratioing actually took 1 minute to calculate on what is a fairly fast computer, so you can't expect these calculations to take a while. Right. Okay, now we've got our emissivity calculated. What else are we going to need? We are going to need to go through these constants here. Now, everything is in meters. So everything is in meters, so we're going to have to be careful about the microns here. Yep, okay, so this is all in SI, meters, kelvins, so we just have to be careful. This is going to become 10.8 to the minus 6. So what I would do here in this case, there's many ways to do this, but I would actually potentially calculate this bracket first. I mean, we could with a lot of brackets, we could actually just go ahead and calculate the surface temperature now. Okay, so in the end, I have decided to take a few steps and go a slight bit more carefully. So if we look at the equation again, it's this silly dialog disappears and we can see the full equation. There we go. So we're going to calculate this expression first, and we're going to name that the denominator, and then we're going to calculate the land surface temperature. So we've got the value of rho, 138, 10 minus 2, the central wavelength of band 10. Remember, these are microns, so we're going to have to put a 10 minus 6 on that. Then it's a fairly simple equation. So I've called this denominator, right? So you can see the equation, and you have to be careful. So in grass, if you want scientific notation, it's lowercase e with 2 decimals. So it's preferable to put the minus 0.6 in this case. So this is the band name, and in the calculator you can just pull this out and it will insert. You can pull this function down and put a map function in. So just be very careful. Reproduce this equation very, very carefully. Right? And the logarithm, so log in grass is the natural logarithm. You can Google that and that'll appear that. And then that comes denominator 1. I've already calculated that. Once that's calculated, then we go back to the equation. We have again the temperature band 10, divided by 1 plus this denominator factor. Right, just here. Okay, let's see. So I've already pre-calculated these. It took about a minute each on my computer. Let's have a look at the results. Now, it is good practice in this case to really go step by step. So I'm first of all going to look at the value of my denominator just to check that it's not an empty raster. Because if it comes up blank, then you know that you're going to divide by it, and it's not going to go well. Right, so I at least have a raster, similar patterns, so that's a good start. And now let's look directly at our land surface temperature. Oops, a bit too keen on the enters there. LST. Right, there we go. We have our land surface temperature. These are surface temperatures. Now let's just do an exercise. Now experience tells these actually aren't going to change dramatically. So here's our land surface temperature. Now I don't expect dramatic change here. You'll see I'm going to get this one. I'm going to do another d dot rast. And I'm going to plot the original to top of atmosphere temperature. Get the same pattern. That's quite normal because the scaling isn't the same. Now, what I actually did is that I took the map calculator, once again, and what I did is I calculated the difference between the two. So very, very simply, you put, band 10 minus, minus the land surface temperature, and I call that, I think, T diff, and I've already got that calculator, so you just do this, something like this, right? Now, if I go here, and then again go another d dot rast, so there's my difference map. So see what's interesting here is that there are certain areas of the landscape where the correction to land surface temperature has more effect than others. It is not a uniform number. That's very interesting. Now, if you look at the amplitude of these corrections, let's plot a histogram, and then we'll do a bit of exploration on the side while this is computing. So the histogram is computing. There we go. It always takes a few moments to compute. There. So there's the curve of the differences that we're observing. They're actually quite small. Temperatures shrunk by 0.02 of a degree, very, very small fractions. If we look, so this bright yellow bit, we're talking about changes of 0.006, and the dark bit, 0.01. So we're talking about 100th, maybe 200ths of a degree at most. So in this case, it was fairly minor over a large area. This has been worth it. This has been, but we do have now a firm land surface temperature. So final point, it is slightly delicate process, right? You have these delicate equations to punch in with the raster map calculator, and you have to be very careful. And one advice I can give is to check yourselves at each step, especially when you've got logarithms involved. If you've made a mistake, you might get completely blank rasters because it might try to do logarithm of a negative or something like that. So check step by step, and at the end, be sure your result does make some sense. And here we do see differences have patterns. Calculate these differences, just do before and after correction. That'll give you some sense. Now, and this is a land surface. If I go, let's have another look at it. Right, let's have another look at that land surface. Because the advantage of this now really is that we have a temperature of the surface. This raster here, right, really is the temperature of the ground, and you can start using that. Let's have a bit of fun here. Let's zoom in on Kanpur, which is somewhere. It's harder to see on this graph. If we look at a city, these are some of the urban cities. Can't see some differences. Of course, these are methods that are going to work better on big cities. You might have an advantage into finding a higher resolution temperature sensor, and you will probably need thermometers underground to validate this. But overall, this is how we can use these remote sensing methods, and they're especially valid for big cities. So I think in India we'll be talking about the big. So of course the big three: Delhi, Mumbai, Chennai, and then going on to some of the upcoming cities, Hyderabad, etc., etc. And that is basically how you go to actual land surface temperature. Okay, finally, just before I go, there is a grass function which was developed by a Chinese group for Landsat 8 called apologies, split window land surface temperature. It is a new algorithm based in 2015. Now it is a slightly more advanced algorithm. The complication is that you do need to go into a Chinese database of land cover mapping. So there might be some extra legwork involved in doing, and you need a cloud masking protocol. So this protocol is more complex, probably more than we have time for in this short course. But if you're interested in taking this further, I do recommend that you investigate. It's a grass algorithm, Landsat 8, SW, LST. Right, so that ends this addendum. So we'll see you in the next tutorial.